Let's explore how microservices architecture applies to big data processing systems. We'll uncover the advantages and key components. We will be discussing the use of microservices in data processing. Here's a comparison of traditional monolithic architecture versus microservices. In a monolithic architecture, we have a single deployable unit with tightly coupled components and a shared database. On the other hand, microservices consist of independent and loosely coupled services, each with its service-specific databases. Monolithic apps are like one big building, while microservices are like a collection of smaller, specialized buildings. Microservices offer several key benefits for data processing. Firstly, scalability is enhanced, allowing us to scale individual services based on data processing demands. Secondly, we get flexibility to use different technologies for different data processing tasks. Thirdly, the performance improves because of the parallel processing across distributed services. Lastly, fault tolerance is achieved, where isolated failures prevent system-wide crashes. In simple words, we can scale up only the parts that need it, use the best tool for each job, and keep the system running even if one part fails. Here's a typical data pipeline architecture using microservices. It consists of three main stages: ingestion, processing, and storage. The ingestion stage is where we collect data from various sources. The processing stage is where we transform and analyze the data. The storage stage is where we store the processed results. Data flows between independent services, for example, from ingestion service to processing service, and then to storage service. Each service can scale independently, and they communicate via APIs or message queues. Let's look at some core data processing services in a microservices architecture. First, the data ingestion service that offers real-time data collection, multiple data source connectors, and data validation and cleansing. Second, the stream processing service that provides real-time data transformation, event-driven processing, and complex event processing. Third, the batch processing service, which handles large dataset processing, scheduled job execution, and resource optimization. And fourth, the analytics service used for statistical analysis, machine learning models, and predictive insights. Let's discuss the two main communication patterns used in microservices: synchronous and asynchronous. Synchronous communication involves direct API calls between services for immediate responses. The code snippet shows a REST API call where a request is sent to the processing service. Asynchronous communication uses message queues for decoupled, scalable communication. The code snippet shows a message queue publish where a message is published to an exchange for data processing. Here are some technologies commonly used in a microservices architecture for data processing. For messaging, we have Apache Kafka for stream processing and RabbitMQ for message queues. For processing, we have Apache Spark for batch processing and Apache Flink for stream processing. For storage, we have MongoDB as a document store and Elasticsearch as a search engine. And for orchestration, we have Kubernetes for container orchestration and Docker for containerization. Here are two common scaling strategies used in microservices: horizontal scaling and vertical scaling. Horizontal scaling involves adding more service instances to handle the increased load. As shown in the code, we can scale out processing service using a command like kubectl scale deployment. Vertical scaling involves increasing CPU or memory resources for existing instances. As shown in the code, we can increase the resource limits for CPU and memory in the service configuration. Let's discuss some challenges and solutions in implementing microservices for data processing. One challenge is data consistency, maintaining data integrity across distributed services. The solution to this is event sourcing, where we store events to maintain data consistency. Another challenge is monitoring complexity, tracking performance across multiple services. The solution is distributed tracing, which helps in end-to-end request tracking and monitoring. The third challenge is network latency, service-to-service communication overhead, And the solution to it is caching strategies, reducing network calls with intelligent caching. Here's a summary of best practices for implementing microservices for data processing. First, single responsibility, meaning each service should handle one specific business function. Second, loose coupling, minimizing dependencies between services for flexibility. Third, data ownership, where each service owns its data and database schema. And fourth, comprehensive monitoring, implementing logging, metrics, and distributed tracing. Microservices enable scalable and maintainable data processing architectures. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.